Ma'am, now you can share your presentation.
Yes, madam. Yes, madam. We'll start.
Yeah, one second. Good morning, all. Welcome back to the day 9 session. Today, in the today's sessions, in the first half of the sessions, we are completely elaborating how to write Verilog code, how to simulate it. In afternoon sessions, you will be having the quiz followed by the assignment. So in order to get the prize, you're supposed to complete the assignment followed by the quiz. So I will hand over the podium to Dr. Suma madam.
Yes, thank you, Dr. Jalja madam. Jalja madam.
Yes, yes.
Okay, good morning to all. I think from past 2 days we are seeing different types of research going on in medical domain with respect to the coding perspective and with respect to the material things. So all said and done, I think it will be better if you have hands-on with what all we know now. And again, my research scholar Namita, whose research is in the field of memory, will be telling you. I think first day only she had told you what are the different styles and how to write and all. Now today, since it is a hands-on, I think it will be better if all of us uh, install the tools in our own systems, or if you are in the college, so that we can simulate our own course and see what is happening, and if there is any issue, we'll be able to correct you all. Since Dr. Jalja has already mentioned that in the afternoon you guys have to submit the assignment along with the quiz. So today's morning session will be like a hands-on, and you guys have to do using your own system or wherever you are, and any doubts we'll be able to help you out. So over to you, Namita, and you can take over. Thank you, Jalja ma'am.
Morning. Okay. Today we are here to give the hands-on on Verilog using models and tool. I'll be doing some simulation for some design, and we'll be giving you some assignments for you to complete by from 2 to 4. By 4 you.
Yeah, one more thing I forgot to tell you, it is not necessary.
One more thing I forgot to tell you, it's not necessary like we need to simulate only in model sim. You can simulate in any of the simulators, Cadence or Synopsys or not. Since model sim is user friendly from Metagraphics, we thought we will just show you so that you will not have any difficulty, but the same thing can be run on any tools. Okay.
So now I'll be starting with the simulation of some basic design. To start with, I'll just take you. We studied some coding styles, that is data flow modeling. In that keyword, the keyword was assigned. Then we have behavioral flow modeling. In that the keyword was procedural blocks, that is initial and always. We'll be using always for the design purpose. Initial we'll be using for the test bench. Then we have structural modeling. In that we'll be calling either the primitives, or we have this thing, primitives or lower module instantiations. Just excuse me for my writing because I'm using the writing board after a long time. That is lower module will be in using in the structural model. To start with, we'll be starting with a basic design. Let's say we'll be doing it for a mux, that is 2x1. So for a 2x1 mux, we have input as, if I take 2x1, we have two inputs, A, B, and one selection line that is also input, but it is the controlling input which will control either of the to flow to the output. So let's say it is 0, 1, and we have y output. So when we say the truth table for this, it is says that when cell is 0, output is A, and when cell is 1, output is B. So we can represent the mux as y A S bar plus S. This is what is the Boolean equation to represent 2 is to 1 mux. Same thing we will be coding it using Verilog now and in data flow model. Now in data flow modeling, the keyword used is assign. So we will start with the data flow modeling. Now to start a Verilog code, we will use keyword module. We'll be writing the same thing on the tool itself. So here we are using the model sim. In this we will create as soon, okay, I'll open the tool. I'll start from the beginning. I hope they shared with you the model sim tool, or you will be having any other tool like Cadence, the ISC. You can use any of the tool to simulate this design. So once you open that, normally we'll create the project for the first time and we'll try to do all our design in that. So file, new project. So I'll just create the project name. Today is Wednesday, BIT. I'll just create with Wednesday BIT, and it is the other directories are the default libraries and everything is there, and we'll do okay. So it will create me this. Either I can directly go for create new file or I'll just close it. So it created a new project for me. Now, once this project is created, if you do right click, it will ask add to the project from here, or it will go to file, new. Again, it will ask you the source. No, sorry, new source that will be in the Verilog. So either go this way or directly click right click, add to the project, new file. First thing, when we go for new file, we will select Verilog. Now I write the name mux2 cross 1. By default, it will take .v because since we can, in model sim, we can write all these languages. All these languages can be simulated using this. So we need to select it Verilog. Now we'll do OK. So it will give me the mux2 cross .1.v file. Now double click on this, it will open the text editor where we can type the code. Right? Now to start with, as we already discussed, the Verilog module, or in Verilog, the design will start with the keyword module, all keywords in a lowercase. Then we will write the module name that I'll take same as what I'm writing the design. That is mux2 cross 1. Mux2 cross 1, then we'll take bracket and we'll define the ports here. As it is said, you can define only ports and do the port declaration later, or you can just define ports and the port types together. So here I'll first define the input A, comma B, then I'll just take one more input as cell. Since this is my controlling input, I am defining it separately, but we can define it together with A and B also. And then we have one output Y. Now, one more thing you can see here, that whatever keywords are there, they are in lowercase, as well as the color is also different. And whichever tool you will be using, they'll have specific color to define the keywords. So all inputs are defined and the output is defined. Now we already saw this design that the Boolean equation, since we are using data flow modeling, in data flow modeling, the keyword is assigned, and we'll be using the Boolean equation to represent the design. So to write that code, we'll use keyword assign, and we'll be using the bitwise operator of Verilog. The bitwise operator was A, and since it was A S bar, not of S, it is cell. Cell I took capital cell. Then or symbol is this thing line plus B and cell. End module. End module. Any doubt? Then first we will save it. Once this is saved, you can see here in the compiling, it will come as question mark status. So just do the right click, compile it. This compile is for any error thing. So compile the selected one. It showed me one error. Now to see some errors, go here. It will be compile report. So if we see here near input, syntax error is there, input expecting. I'll go to this line. Input, here I just input comma because it is A, B. I have one more thing, so I have to put comma over here. That's why that was missing. So any errors will be visible there. You can come back, do the correction, again go back here. You can close this window. It was, then again select compile selected, and now the status says it is correct. Any doubt? Now we can read here in the transcript, compile of 2x1 was successful. Any confusions? Any confusion? Should we go with simulation? Could anyone please respond like it is? Is it Vivado or Vivado also you can do the same code. The thing will remain same, only the this thing steps will be different. If you have Vivado, you can simulate the same thing will the simulation. Okay. So now once this is done, either now we have to go with the simulation, means we can go to library. There are two ways to go for simulation. Once we'll be using the tool itself to force the values. The other way is we are using the test bench to do the simulation. First we will use the tool and then we will write the test bench. So once this is done, we'll go to library. In our work clip, we'll be having this will show, this work clip will show all my design. So this was the thing what we did today. So here I'll just do the right click and then it will be simulating it. Select your design and simulate it. Just minimize this. You will see all the inputs in the objects. There will be one thing correct done given as object. Select that objects, all the objects from the object windows. Just select all the objects from object window, do the right click and then add wave. Again I repeat, once you do simulate, all these windows will open. Go to object window, select all this by selecting one by one by pressing control, pressing shift, right click, add wave. It will open the wave window with the all your signals. Now since we are using tool to force the input, we will just select A, we'll force it, right click, select the input, right click, force. It is the signal name, it is the for simulation, the design name is here, which signal we are forcing name is there. This is the value. We already saw that in Verilog we will represent the values using size, tick, base, tick the value. So it is taking 1 bit size. We are representing in hexa, or we can use binary. Since we are more comfortable in binary, we'll just write 0 here. We are giving A as 0 and we will give OK. Similarly, we will select B and we will right click, force the value and we will give here as B1. We'll say OK. Cell we will select and we will again force cell to be 0. Now what we will this all three values are forced and output is y. So we'll not force any value. Once we run the simulation, the output should be updated as a will show x. So now from here we can see this is a run button, and if you run from here, it will be running for 100 nanosecond, because the scale here, what time period we gave is 100, so it is 100. Now if you see, cell is 0 and the output what we are getting is 0. So according to our code also, what we wrote is here, if cell is 0, it should be A. If cell is 1, it should be B. That's what we say here is also, when cell is 0, it is A. So when cell is 0, we are getting 0, so it is 0. When I force now cell to 1, I can use hexa also, no problem. Then if we see here, since cell is 1, output is getting updated to 1 because B is 1, A is 0. That's how we are verifying. You can still change A to 1 and B to 0 and check it. This is what is the basic 2x1 mux design using bitwise operator. Any doubt? Any doubt? Okay, so now on the same design, I will change the value. I'll close the simulation. This is done. Now I'll open it. If you remember, that day we taught you that it is conditional operator. It is using assign only, but we'll be using, see, mux 2x1 will be used at many places. So this design should be very much clear to all of us. Now the same thing, inputs and outputs will remain same, but we'll be using the conditional operator. So we'll write assign. The conditional operator was this. It says expression. Then we'll have true expression. If it is 0, we'll have, if it is 0, what it was, y is equal to cell. If it is 0, we will true, we'll have true expression. Otherwise, we will have false expression. This is what is your this thing. So assign y cell. If it is 1, we said it is B. If it is 0, we say it is A. That's what. When it is true, this is true expression. This is false. False. True expression means when it is 1. False means when it is 0. So that's what we are writing here. So same code I am presenting. Now, as we know that to comment the line in Verilog, we will use double slash. So I commented this line, and now I am using assign y equal to cell question mark. It is true means B, false means A. We will save it. Once you save it again, we need to go to this is again question mark. We need to compile it. Compile selected. This is successful. Again go to library, select this, simulate it. Come here, select all the objects from the object window, right click, add wave. Again we will force it to, it's a bit slow, force it to 0. Okay, force this to 1. Same procedure, cell, force it to 0 first and then 1, or vice versa, and done the simulation. So if you see here, it is again saying that cell is 0. So since A is 0, it is giving a 0. Now we'll force cell again to 1. So it is showing me 1. So the code is same. The design is same. The only way how to write a code is different. Either use the bit So whatever it is, input will not be 1 bit. So we will have like this mux, cell will remain same, but input can be of n bit. Each input should be of n bit, and even then output will be of n bit. This n can be of 32 bit, it can be of 64 bit, it can be of 16 bit, 8 bit, or some 128 or 1024. This type of design we called as overlapping muxes. When we have more than one mux, 2:1 mux, and it is mostly used when we have to pass a input which is more than 1 bit. So now when we have to design this mux, this is 2:1 mix only, but it is overlapping mux because input is not a single bit, it is more than 1 bit, that is n bit. So let's say we have to design it for 4 bit. So now what we have to do here is A, B, Y. Cell will remain this thing only, but this will be 4 bit, this will be 4 bit, and this will also be a 4 bit. Because then again it says when cell is 0, y is equal to A, when cell is 1, y is equal to B, but this each will be of 4 bit. So now how to code it? Coding will remain same. The only thing is the definition of input and output will change. Coding style we are not changing. The definition of input and output is changing. It says that I am changing in the same code because it will be, so now A will be how many bits? How to define a vector in Verilog? If I say any vector, it has to define in the bracket. It is n minus 1 colon 0 or n colon 0. Anything can be defined here. So whatever is the bit, if n is 16, I'll take, if n I can take 32, I can take 43, whatever number of bits you want, you can put n equal to that much. So now I'll just change the code to 4 bits. So I'll define input as 3 colon 0. Since we are using 2:1 mux, we need 2:1 overlapping muxes. So both input A and B will be 4 bit, that is 3 colon 0. Even the output will be of 4 bit, that is again 3 colon 0. That is Y. This part will not change anything. It will remain as it is. Because cell will be of 1 bit itself. When cell is 1, it is B. When cell is this, it will be 0. The only change will come in the sizes. And this will be nothing but the overlapping mux. Again, I will save it. I will compile it. Just a second. Projects, I can compile it. Again, it got success. It is successful. So I'll come to the simulation window, library. I'll simulate it. I'll select all the objects from the objects window, add it to the wave. Open the wave window, force it. Now you can see instead of 1 bit, previously it was 1 tick H. Now it is 4 tick H. So I'll just give 4 tick H. I'll give 0 here. Okay. I'll force it to 4 tick H. I'll give F here. So all ones I'm putting to B. I'll give cell as 0 again. And we will run the simulation. So you can see this thing here. Now I will give cell as 1. Again, I'll simulate it. You can see F. So again, it says that when cell is 0, it is giving us A and it is passing all the 4 bit. When cell is 1, it is giving us B and it is F. Yeah, right. And we can change here as radix here. This is like you can select all the signals together or one by one. Right click, you can see radix. It is here as binary. So you can see even in the binary the same thing. So we can see that all 4 bits are transferring to output. This is called as overlapping muxes, and this is widely used in digital circuit because whenever mux is the widely used block of digital circuit, and we have to pass the input which is more than 1 bit, it can be any number of bits, and that many number of muxes will be created. So we normally say this is 4 2:1 mux, 4 bit 2:1 mux otherwise, or 4 2 is overlapping 2:1 mux. Any can be called by to this. So like that it will be this thing. Any confusion, any doubt? Do you want me to tell anything again? Do you want me to repeat anything? Please let me know, one of you. Otherwise, I'll go for the next design. I'll just wait for 1 minute.
Dear participant, if you have any clarification directly, you can interact with the speaker. Based on morning session, you will be having certain assignment followed by the quiz question.
Because you will be giving you few questions on base on this, and then you have to complete it. So you should be thorough with the assignment. You should be thorough with the design so that you can complete your assignment on time, as ma'am said. Yeah, if you are talking about FPGA processor, you can select any because you are not downloading as of now. For simulation, you can go with any FPGA processor. You can select. I think it will start from not Spartan. It will show you basis the Arctic 7 series. If you are having Vivado, you can select any Arctic 7 board and start the simulation. I think I have a Vivado also with me. It's here. If it is there, like, but due to some license issue, my simulator is not working. Otherwise, I could have shown you the simulation on that also.
Ma'am, Vivado is required license, or we
Yeah,
can
it
install
is.
it?
No, some simulation license are required, ma'am. That's why
License
my
are required.
simulation is hanging there. I tried that yesterday,
Oh,
but
fine,
it
fine.
was hanging. That's why I was not able to do this. Should I go with the new design? Okay. Now, because this mux is very important, so we'll go for one more design using mux, because this is the base. You can design anything later with this thing. Now next what we'll be starting is the basic gates using mux. Once we know the basic gates, using mux means we can design any digital circuit, because gate is the basic block, building block of the digital circuits. So now let's say AND gate. AND gate means we have two inputs, one output. I'm going for two input AND gate, 0, 0, we'll say 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. Now this AND gate I need to design using mux. using 2 cross 1 mux, because we are 2 cross 1 mux. Now in 2 cross 1 mux, we have 3 inputs, A, B, and cell, as we already designed, and one output. So output is there with us, but we need to try and fix these 2 inputs of AND gate A and B to these 3 inputs. So what we will do, we will try to find the solution of that. Now, what is the control element for a cell? When cell is 0, we are taking A. When cell is 1, we are taking B. Here also we'll try to do the same thing. If we see here, when A is 0, 0, in this 2 case, irrespective of B, whatever is B, 0 or 1, output is always 0. And when A is 1, if B is 0, we are getting 0. And when B is 1, we are getting 1. So we can say the output is B. And I can divide it over here. So what we have taken here is, we have taken A as some controlling element. We are checking A, what A is actually. When A is 0, it is 0. When A is 1, it is B. When we have anything, when like A is controlling and we have 2 options at the output, either it should come 0 or B. So this will result in 1 mux. This can be designed using 1 mux. And what we are doing here, same thing what we did in mux. We are putting A as the selection line. When A is 0, we are tying it to 0 itself. And when A is 1, it is nothing but B. And this is what we are getting at. So there is no change, only change is one input is missing, that is cell we don't want when we design 2 cross this thing, 2 input AND gate, and we are just designing the using mux this thing. So I'll just change it. Okay, could you try the code for this thing once and just type it, show me one line code. I don't want you to type all the codes and all that. I'll understand that you will be doing it. I just want you to show me the basic assignment statement. I'm using again data flow modeling. I didn't change my modeling style yet. Could you just type in the chat box? By that time, I will also create my new file. I'm also writing only this thing. I just want to check how many of you are writing that. By the time I'll finish my definition of this port declaration. That's it. Any idea? I'm waiting for it's just one line. You write anything, I'll understand here. Please let me know. Is there any result? I can't see anything. Am I audible to everyone?
Yes,
Then
ma'am.
could you please try once? At least give me some hint. Okay, I'll give you this code, but I want another one for you to write and show me. So again, since we'll be using conditional operator, I'll use a keyword assign y. Now, conditional operator means we have to check which input is deciding the output, flow of the input to output. So this is nothing but A. When A is 1, it is B, otherwise it is 0. So here when we write the code, we will say A. This thing y is equal to what? Decided by A. Design, when we write a code, we'll start with keyword module. Here also we will start with the keyword module. Afterward, followed by module name. Here also it will be followed by test bench name. When we write a test bench name, we will write such that mux, suppose I'm writing 2 cross 1, I'm writing for AND gate using mux. I'll differentiate it with TB, writing TB, or I'll write like TB underscore mux 2 cross 1. So I can understand this is a test bench for this basic design. And like in we have all the ports, here we will not define anything and we will end it as semicolon. The other thing is after this is all the inputs of your DUT. Like suppose 2 cross 1 was, we have 2 inputs and 1 output y. All the inputs will be declared as reg and output will be declared as wire. If you're not comfortable initially with writing test bench, you can follow the same procedure for simulation. It is just for showing you. Once the practice will be there, it will be clear. Test becomes more easy for us instead of forcing the values. So reg A cross B, then wire Y, then we will instantiate our design inside this module by the same name. So what was the name we gave in the instantiation? We gave the same module name mux 2x1 and we'll give the instance name, and then we'll map this ports, map the data, all the signals with the ports of the design. So we have A, B, Y there. And it should be in the same order. A should map to A, B should map to B, and Y should map to Y. Suppose if I write here X1, X2, and Z, I should write here as X1, X2, and Z. I should not use A, B then. These are the actual ports, these are the formal ports. So formal ports, these are called as formal ports here, should be mapped to the actual port, but the order should be same. If formal port X1 has to map to A, yes.
Madam, the audio is not clear, madam.
I didn't get you. Your voice is breaking. Could you?
Madam, the audio was not clear.
Hello? Audio was not clear before also.
No, just from the start, test bench.
Oh, from the start of test when only other. Okay. Okay. So what we are doing, I am starting with the test bench. A test bench is nothing but it is a wrapper around the design. It's a wrapper in the sense through test bench we will force the inputs and we will check the response. It is same way like how we suppose we are rigging up the digital circuit on a breadboard. Or now also when we simulated here, if I see here, we were forcing this 0 and 1 from the waveform window. This will not become good if we write a big design, forcing this value and checking one by one result. So in testment, we will force this into the design and check the response on this waveform. So instead of using this tool to force the values, we will be writing the test bench, and in the test bench, we'll be defining or we force all these inputs. So to write a test bench, we have to follow some rules. I'll start, otherwise, I'll write the code directly on the model. So I'll just stop the simulation. We'll go to project. In the same project, like how we went for the design, I'll go add to the project new file. In new file, first we will select Verilog. Then we will write PB. For what design we are writing, please give the same name. For whatever test bench, you can use any name, but it is always good that we will write the same name. That is marks 2x1 and. But name should be different. In the same project, we cannot do the same thing. So that's why for writing test bench, I have differentiated the test bench from design.
I'm sorry for the disturbance. Hello. Ma'am?
Hello?
Ma'am, your voice is, I think,
Yes.
is not clear. Your voice is not so clear.
I can't hear you, madam. No.
Hello?
My voice, hear the net. Hello, am I audible now?
Yeah, now you are audible properly. If you go to that
But your voice is
yeah, that
only breaking for me.
okay. Okay, ma'am, you can continue.
Am I okay? Am I
Yes,
audible
yes,
now?
ma'am, you can go ahead.
Okay. So we got wrote with test bench underscore mux 2x1 because I'm writing a test bench for this particular design, and I'll say okay. Again, it will open me this same design. I'll click here. Writing test bench is also starting with keyword module. You have to give module name. Module name I'll keep the same as the design name. So for me to distinguish, it becomes easy. So mux 2x1 and that much, not dot v. And then we will just put this semicolons, bracket and semicolons. If we compare this with a design, if you see here, if we see, is it visible to you? Now, in this design, we were writing the ports, but here we are not defining any port, it is empty. The next is whatever are the inputs in our design should be reg there, and whatever is the output in the design should be wire. So A and B were the two inputs, so we will declare input as reg, semicolon, output as wire, semicolon. Then we will call our design into this test bench, because automatically the test bench is forcing the values to the design. The design should be called by the same name. So I'll copy this name as it is. Module name followed by the module instance name. This is the user defined name. You can give anything. I'll just write DUT. It says design under test, which is the design for what we are writing it. Bracket, we need to map the register A, whatever is our formal port in the test bench, to our main port. The first input is A, second input is B, third is Y. So I'll be mapping A to A, B to B, and Y to Y, semicolon. Am I audible?
Yes, ma'am.
After that, we need to write force the value. This is what is the basic thing every test bench will have. Now I will use one procedural block to force the values A and B. The procedural block will be the initial. We have two procedural block in Verilog. One is initial, the other one is always. Always is used for a different purpose. Initial, since is execute only once, it is the best used in the test bench. Because once we'll force the values, we will simulate it, and then we are done with the verification. So initial, begin. Now initial, it will start with the time 0. So I'll give A is equal to 0. I give two equals there. A equal to 0. So I should write one tick B 0, semicolon. That at the same time we should force B also to be 0. So this initial block will start at time 0, and initially when we are giving both A and B as 0. Then we'll give some delay, let's say 5, and I will give, I'll just copy this line so that I can type it again and again. Then we will force at 5 unit of delay, we will make A as 0 itself, but B we will give 1. Again, we will give B as 1, A as 1, and B as 0. We'll give one more thing, and we'll give both A and B as. Since we have begin in the initial, we will end it, and the ending of this module will be end module. So we started the test bench with keyword module, we ended with end module. All inputs are declared as reg, all output should be declared as wire. We instantiated the design, we wrote one procedural block through which we are forcing the values inputs to our design. Now we will save it, the procedure will remain same. Again, we'll select this, we'll compile it. So we can see here compile of test bench mux 2x1 n.p was successful. Go to library. Now we will not select this, but we have to find this design tb underscore this thing. So this is here what we created. The same name we have to select, tb underscore mux 2x1 n. Right click, simulate. So I'll select again from object window, I'll select all the things, right click, add wave. Now in the wave there we were forcing the values initially. After clicking here directly I will run. So it will run all it together. If you see, I just zoom it. You need not force it. See here 0 0 0 1 1 0 1 1. Since we retained the last value as 1 1, whatever time you will simulate it now, it will be 1 1 itself. This is what is the test bench. Otherwise we were using tool to force the values. Here we are not using tool to force the values. We are writing the test bench, we are giving all the values and we are running, and this test bench will be saved with us. Anytime you are changing anything in the code, you just need to run it. You need not come back to the tools and force it. This is about the basic test bench. Any doubt? I'll just wait. Any doubt? If you are not okay with as of now with test bench, we'll be forcing the values. This is just I wanted to show how the things will be done using test bench. Okay. Next is that model sim download link. I think Jalaja ma'am will be providing you. It is there with them. Ma'am, are you providing them, Jalaja? Maybe she's okay. We'll check with her after some time. Okay, the next is I just want you to give me a code for XOR gate using 2:1 mux. I'll give you 2 minutes to think on that. Like I just want one line assigned y is equal to how it will work. I don't want all your inputs and output posts. That you can do now. After that, we'll go for the next design. Anyone? It's not that tough now. I want you for XOR gate. So you can try practicing as an assignment. You can just and with it XOR. So you can do for or, nor, NAND. Any answer? A1, it's B bar, else it is B. I think you wrote B bar, correct? So when I say it is A, B, Y, 0, 0, it is 0, 0, 1, 1 it is 1, 1, 0 it is 1, 1, 1 it is 0. So 0, 0, again I'll take A as the controlling element. So if it is 0, 0, when B is 0, it is 0, when B is 1, it is B, so it is B. When A is 1, if it is 0, it is 1, when it is 1, it is 0, so it is nothing but not of B. So it's correct. So it is when A is 0, when A is 0, we are getting Y as B. When A is 1, we are getting B bar. So I can, in Verilog, we can use assign Y, the controlling element become A. When A is true, it is B bar. When A is 0, so I'll write B bar and it is B. So you'll get an XOR gate. So this is about the basic gates using this thing. Now, is there any doubt in designing mux, 2 cross 1 mux, overlapping muxes, gates using mux? No confusion, correct? Any other answers? Okay, next we will go for, so this all three we finished. Now we will go for the comparator design. In digital circuit, we have to know 2-3 blocks very thoroughly: mux, comparators, adders. Then we'll go to design of sequential adder and deflux. If you know these 3-4 blocks, you can design many digital circuit around it. So the next one is comparator. Comparator is a block where name itself equals, it will compare the two inputs and it will give the result as whether the input is greater, equal, or less, which input is greater. So here what I'll do, again I'll take a box. This design we have to do. This is the comparator. We have two inputs, A, we have another input B, and we will have A greater than B, A less than E, or equal B, or A can be less than B. Or you can write B greater than A, B equal B, B less than A. It's your choice. You can take anything, any input as first or last. Now, as of now, A and B are 1 bit each, and these three will always be 1 bit output. So if it is 3 bit, 1 bit, we'll have only 4 combination of available vectors: 0, 0, 0, 1, 1, 0, 1, 1. We have 3 outputs with us: A greater than B, A equal B, A less than B. If it is 0, 0, what should be the output? If it is 0, 0, this should be 0, this should be 1, this should be 0. If it is 0, 1, it is A less than B, so 0, 0, it is 1. If it is 1, 0, means this is 1, this is 0, this is 0. 1, 1 means 0, 1, 0. So we can just write A greater than B as A B bar, A less than B as A bar B, and A equal B as A X naught, that is A B bar, A B plus A bar B bar. It is nothing but X naught when it is 0, 0, or when it is 1, 1, or NOR of A greater than B, A less than B. So to code it in Verilog, we can use normal data flow modeling, assign A greater than B, A less than B, A equal B. We are done with this. Now when we go for 2-bit comparator, now as comparator will not be only 1 bit, comparator can be again of 2 bit, it can be 4 bit, it can be 8 bit, it can be 16 bit, 62 bit, 64, 32, 64, like that. It can be of any n bit. How to design comparator using this traditional method? Because this is a traditional method to design the digital circuit, and same method we were putting as the data flow. But data flow modeling becomes complicated once the number of input increases. So what we can do here, we can use the structural modeling. What was the structural modeling? One was behavior modeling. When we do not want any hardware, we'll just put A greater than B. But this is not the proper way, because we'll not be aware of the hardware. It is the highest level of abstraction, and we'll not come to know exactly what blocks are coming in a circuit. So we will try to do this using our structural modeling. When we have 2-bit comparator, we'll be having A as A1, A0. Let's say B as B1, B0, and the output will be same as A greater than B, A equal B, and A less than B. Now, when we design comparator, first thing is, suppose I give you these two numbers, even if though they are decimal. Suppose if you know this number, let's say this is 4, this is 5. Can you tell me which number is greater and which number is less? Can we predict the result? Which number is greater or which number is less? Sorry, I need your answers. Can we predict the result? I need the answer, please. If you know these two numbers, unit numbers, This is A1, A0. This is B1, B0. Suppose these two numbers are known. Or same thing if I give you suppose this number. Instead of this A0 and B0, if this is A1, A0, B1, B0. This is 4, this is 5. In which condition you can tell me which number is greater, or in the first case can we tell which is greater or less? Can we tell it? Answer you can type, but it hardly takes seconds to say yes or no. Can we tell it? I just said if you know this is A1, A0, B1, B0, if you know A0 is 4 and B0 is 5, can you tell me which number is greater? A is greater than B or A less than B? Can you predict the results? Only if you know A0, B0. Let's say this is case 1 when you are knowing A0, B0. Let's say this is case 2 when you know A1, B1. A1 is 4 and B1 is 5. Can you predict the result now? In which case can you tell that it is case 2? Okay. Any other answer? Case 2 predictable, but case 1 is not the predictable because we don't know what is A1, A0. But once we know MSB, we can tell that A1 is greater or A1 is less. In this case, obviously A will be less than B. Here we don't know which is less, which is greater. If I put 5 here, 4 here, it becomes A greater. But if this is 4, this is 5, A becomes less. Like that, if we start with LSB, we can't predict the result. But at the same time, in comparator, if it is more than one step, right? If we start comparing it with MSB, we can say if we our only thing is if suppose both are 5. Now you cannot tell whether A is greater than B, A equal B, or A less than B, depending. Then the decision goes to A0 and B0. So we will take an advantage of this and design a physical circuit. Now we have to divide it. We have to divide our bits because we are comparing bit by bit. So we know, and already we have our 1-bit comparator with us. So I'll take 2 comparators. Let's say this is our comparator of 1 bit. Again, I have comparator 1 bit. Now, to this comparator, we will give A1, and to this comparator, we will give B1 because we have to compare these two, and we will give B0. Output as it is A greater than B. I put 1 because we are putting it for A1. A equal B1, A less than B1. Here I will give A greater than B0, A equal B0, A less than B0. Now suppose when I compare A1, B1, I got this as 1. I got A greater than B1. If this is 1, should we go and check A0, B0? No. If this is 1, whatever is this answer will be a final answer. So what I can say here is I'll put a mux. As I said, we'll be preferring a mux based design. If A greater than B is 1, no need to check anything. We will say the output is A greater than B. What it is, let's say these are all bits here. We will pass these 3 bits as it is. So what bits we are passing? A greater than B1, comma A equal B1, comma A less than B1. Because this will be 1, this will be 0, this will be, and that should be your final answer. Final answer is A greater than B. Let's say this is A less than A equal B, A greater than B. So this should be 1, 0, 0. If suppose this is 0, 0, 1, if this is not 0, so what we will check? We will check A less than B. A less than B1. If this is 1, what should be our final answer? It should be again as it is. Our final answer should be 0, 0, 1. So again, we will pass this 3 bit as it is through mux, that is A greater than B1, A equal B1, A less than B1. Suppose if this is also 0, if this all 3 are 0, if this all 3 are 0 means obviously A equal B1 will be 1 because this is 0, this is 0 means this will be 1. When both are equal, we have to go for A0, B0. And whenever whatever is the result coming through this A0, B0 will be our final result. It means we have to pass this 3 bit as it is. So we'll be passing A greater than B0, A equal B0, A less than B0. Yes, I asked. It's clear, this design of 2-bit comparator. Is it clear? What I did, I asked you which 2 cases you can tell. So you all said it is case 2. In case 2, so now we are giving priority to A1, B1 as you people said. Case 2, if we know, we can answer. So we have compared in case 2, we have to compare A1 and B1. So we started comparing A1, B1. We got A greater than B1, A equal, A less than, and our final output is A, B. Our final output remains same, either A greater than B, A equal B, or A less than B. We need to know only this thing. So when we are comparing these 2 bits, we are getting this result. When we are comparing A0, B0, we are getting this 3 result. So in A1, if A is greater than B1, we have to give output as this itself, because 1, 0, 0. If suppose this is 1, this is 0, means we are getting A greater than B, and we are passing the results from here as it is to the output. If this is 0, we are checking whether A1 is, because if this is 4 and 5 or 1, suppose this is 1, this is 0, we say A greater than B. But if this case is not, we will check whether it is 0 and 1. If this case is true, means A less than B, so we will pass as it is this one. But even if this both are, then the last cases means when they are equal, either it is both 0, 0 or 1, 1, in that case this will be 1. So if equal means we have to see the result from A0, B0. So whatever is the result coming from here will be our final result. So we are passing this bit as it is. So same thing, now we will try to code it in Verilog. Okay, so we will close this design as of now. I'll close this also. I'll go to model sim. I'll close the simulation also. I'll go to project, and we will do the right click, add to project, new file. We'll start with comparator. Comparator 1 bit. We'll select the file as Verilog, and I'll say OK. I will select it, module. I'll give the same name, comparator underscore 1 bit. Input, since it is 1 bit, we'll have 2 inputs of 1 bit each. We have already discussed the design. We have 2 inputs A and B. We have output A greater than B, A equal B, A less than B. Now we will use again the data flow modeling. Already equations are shared with you. We'll be designing this part, A greater than B, A less than B, A equal B. So same thing, I'll be coding it now using the Verilog. So A greater than B equal to A and assign A equal B is equal to A XOR B semicolon. It is 0 0 1 1 1 0. So I'm using an XOR operator, not of this. Then assign. You can try other way also, no problem. We can write the code in many ways. A less than B equal to not of A and B and module. This is done. And module. So this is comparator 1 bit. I'll just save it. I'll just compile it. Go to project. I save. I'll compile it. Again, it came some errors. So I'll just open it with the compile report. Near syntax error. Near this. Semicolon. Wait. I'll just open the code. Here it is saying it is not the semicolon. We should not put semicolon because it's the end of line. So I did a mistake. It should be comma. So it should be saved now. Again, I minimize it. I'll just close this report. I'll just compile it. It is now successful. So any error, if it is there, it will show you. You have to go there and correct it and again simulate it. Now instead of writing the test bench, I'll just again use the simulator to force the value and check it. So I'll be selecting comparator 1 bit. So I already have this note. Wait a minute. Comparator underscore 1 bit. So this was my design comparator underscore 1 bit. I'll just write it, simulate it. I'll just select all these inputs and outputs, add weight. This I think the procedure will be clear to you now. We'll force the value. I'll do A as 1, B as 0. So it should be A greater than B. So I'll run it. So we can see that A greater than B is 1, all others are 0. Now we'll force this to 1. We'll run it. So we'll see that A equal B is 1. Now we'll force this to 0. And we will run it. We'll see that A less than B is 1. If you see that it is A less than B is 1. So we can see here it is A less than this thing, A greater than B, first A equal B, and then A less than B is 2. So similarly, if I give again here 0, as I have to check the entire all the inputs, again A equal B will be 1. So this is a comparator 1 bit. Input 1:0, we have 1:0, we'll define a comma b comma, we have two inputs, 2-bit each, so I wrote a comma b. Then we have output a greater than b. I'll take the same output, a equal b, but here a and b will be 2-bit each, but output will remain as it is, that is 1-bit each. So this is what. Now we have to see our same design what we have done here. We are calling this. So we will go for structural modeling. We are mixing the comparator 1-bit. We did using data flow. Now we go for structure because we have already built design lower module in the upper module or in the bigger design. So now we call this comparator 1-bit twice. So we'll name this as C1. We'll name this as C0. This is our main inputs. A and B we already have. These are our main output. But we need this intermediate signal because we'll be assigning the main output depending upon this. So we will be declaring all the intermediate signal as wire in our design. So wire A greater than B0, comma A equal B0. I am naming in such a way that we can understand what from where we are generating which output. This is 0, then A greater than B1, comma A equal B1, comma A less than B1. So since comparator 1-bit we are calling, it has two inputs A and B, and it has three outputs, A greater than B, A less than B. So that's why we need 6 wires. So we have called it as like the 0. Now I'll call the design. So I'll be calling it with the same name because we should not change the module name, otherwise it will give error. It will say that this particular design doesn't exist in your with you. So I'll call C1. I'm calling it the first one. So I'm calling it with C1. C1 in this. Yes, any doubt? Your voice is breaking. Who wants to say? Jansi, some. Is there anything you want to say?
ಈಗಿನ ಸ್ಟೂಡೆಂಟ್ಸ್ ಹೆಂಗೆ ನಾವು ಹೋಗ್ಬೇಕು ಫಸ್ಟ್ ಬೇಕು ಅಂತ ಬರ್ತಿದ್ರು ಈಗ ಓಪನ್ ಆಗಿಲ್ಲ.
Is it too? Is there anything you want to tell? Hello. Yes. Is there any confusion? Please let me know. Okay, so I was calling C1. See, when we call C1, we are mapping A and B of comparator 1-bit to A1, B1, and when we are calling C0, we are mapping comparator A and B to A0 and B0. And the output A greater than B is mapped to A greater than B1, A equal B is mapped to this, and A less than. So, what we are calling in this, the order is A, B, A greater than A equal. So, same way we need to do the port mapping here. So C1 is mapped to A1, comma B is mapped to B1. Here in further state, A greater than B is mapped to A greater than B1. A less than B is, then we have A equal B, so A equal B1. Then we have A less than B1. Similarly, I'll call one more comparator with C0. I'll call it as C0. Then I'll map A of C0 to, or A of comparator 1-bit to A0. Then AB of comparator to B0 and A greater than B1 to A greater than B0. A equal B to A greater than B0. So A less than B to A less than B0. Now we need to design this part. If A is greater than B. Now see, we are again going for mux only, but we are saying that A greater than B1. The conditional operator should check condition on A greater than B1 first. If that is true, we have something to do. Otherwise, have to go for A less than B. So I will name this as one signal here. This also I will need one signal. Let's say this is Y or W1. So I can use assign. Is there something someone wants to say to me, or there is some noise coming? Is it for me or someone? A greater than B, A less than B, put semicolon, put equal. I was audible, correct?
Yes, ma'am.
Okay. So now 1-bit comparator and 2-bit comparator design is over. Now the next assignment for you for the afternoon is 4-bit comparator. Please make a note for this, and using 2-bit comparator. You need to design a 4-bit comparator, and you can use 2-bit comparator as your building block or to design 4-bit comparator. We need the simulation. I think ma'am will be sharing the format. You have to write the design name. You need to write the code and the simulation waveform, screenshot of the simulation waveform, what you are getting. You need to design 4-bit comparator using 2-bit. Already the first assignment was a basic gate. I can use NAND, NOR, and X. I wrote this here. It is NAND, NOR, and OR. The second exercise or the assignment is 4-bit comparator using 2-bit comparator design. Is there any confusion? Should I wait for 1 minute? If you want to just see the code, I'll just open the code here. You can go through this code once. Okay, so this part is also done. Now with this, I'll add one more exercise. One assignment 3 also, or exercise 3 also I'm giving you. You need to design 1-bit full adder using data flow modeling. 1-bit full adder, I'll give you the box here. Inputs are A, B, C in. Output is sum and C out. So you need to design 1-bit full adder using data flow modeling, and inputs are A, B, C, output is sum. Using this 1-bit full adder, you need to design a 5-bit triple carry adder. It means in Verilog, we have to go for structural modeling. Is there any confusion? Code for 1-bit should be in the same project. Correct? Yes, you should write both. When you are doing structural modeling, all your lower module should be in the same project. If you change the project, it will not recognize that design. Okay, the next design what we will go is for flip-flop. So now we have to go for the flip-flop design. That's why now this already mux, comparator, adder. The 3 blocks you will be doing it. Comparator you're done. Adder, since we are using it from long time, you know the ripple carry adder. You understood how to write Verilog designs. You can do that. That's why we are not writing the code for this ripple carry adder. So the next design what we need to go is for the flip-flop, so that you can control the timings easily for any circuits. So in the basic thing, like how the combinational, the basic block is mux. Here the basic thing is D flip-flop. Whatever we do, whatever you do, you need D flip-flop. What actually D flip-flop does? whatever we have at this here, whatever combo logic or whatever is sitting here at this input will come at the output whenever the clock will come. So it is controlling the flow of input to output by this clock. That's what. There is no other functionality or extra functionality defined by the D flip-flop. Only it is controlling the timings. All this combinational circuit, whatever design we want, can be done using the mux, adder, and comparator. Whatever we have to design will be designed using these three blocks what we have studied. So now we have to see how to code D flip-flop in a Verilog. In D flip-flop, so we have input D in. This input D in directly as of I am now taking externally, otherwise it can come from any combo logic. Then we have main thing synchronizing signal as clock, and the other signal what we have is the reset, and we have output of D flip-flop. So in Verilog we have to code it, this part properly. So now we will start with module. Okay, I can write the code itself directly. New project, Verilog, D flip-flop, D flip-flop. So we will again start with the keyword module, D underscore flip-flop. We have all our, since I wrote capital D, I'll normally use the same file name. You can use different module name, but I have practiced to use same. So D underscore flip-flop. Now we'll define the input. So input of the D flip-flop will be clock. First thing, then we have reset, and we'll define the input to the D flip-flop as D in. Then we have one output. Now output Q. One more thing here. To design D flip-flop, first thing is we need to use this edge trig. We have to recognize what we are doing. We have to assign Q, D to Q. Then whenever this clock edge will come, so this clock edge will be recognized by the always block. We have to go for the behavioral modeling, and in behavioral modeling, the keyword is always. So always at, now this edge in Verilog, we have one keyword to declare, to detect this positive edge, and that is nothing but pos edge of clock. If we assign anything inside this pos edge of clock, it says that whenever the edge is coming, then only input is going to output, or it says that it infers a D flip-flop in hardware. So pos edge of clock will be there, and same thing when the positive edge is coming, we are assigning. But if we need to detect the negative edge, for this we'll be using the neg edge. So this is pos edge and negative. All other inputs will become part of this always block, but the main synchronizing signal is this, and whatever we are assigning inside this pos edge of clock will infer a D flip-flop in hardware. So I should take here as pos edge always. This is the main block in the behavioral modeling at, but this always block will trigger only when the positive edge of clock will come. It is not a level trigger. For always block can be triggered using the level signal also, but this is using the edges. So I'll write pos edge of clock and this thing. Now once the pos edge of clock will come, we have another signal called as reset. If reset is active, see here I can say that we have D flip-flop here. When clock will come, it will check what is the input. But if reset is active, the output should be 0. If reset is not active, then it should be D in. So the controlling, it is decide whenever the edge will come, the reset will decide what is the output. So since reset is deciding, we'll have one mux at the input, we'll have reset. When reset 1, we are saying it is 0. When reset is 0, we say it is D in, going to the output. So this is nothing but a D flip-flop design. So it depends on the reset signal now. If reset is 1, it is straightforward 0. Only when reset is disabled, it is 0. So now, since I'm writing here, so passage of clock, I have to check reset. Now I'm using the always block. I can use conditional operator also, but since we didn't use if statement, I just want you to use if statement. So we'll check for reset condition. However, how the conditional operator gave us 2:1 mux, one if else condition will also give us the 2:1 mux in hardware. So if reset is 1, we are assigning q equal to 1 tick v0, else we are assigning q to be b in end module. So this is all the inputs used. Now there is one more thing to check here is, since we are using behavioral modeling procedural block, we are assigning the output inside procedural block. We need to declare the output as reg, because inside procedural block only the reg variable can be assigned, not the net data type. So here we should declare output as reg. Still in data flow modeling, in structural modeling, we didn't touch reg type, but whenever we are using the behavioral or the always block, we need to declare the output as reg, and that's what we did here. Output reg q, and always at passage of clock, if reset q is 0, else it is d end module. We will save it. Again, we can write the test bench, but I'll show you how to use the tool. Once you're familiar with the tool, we will write the test bench for the same thing. So now this is done. We will compile it. It is done. We'll go to the library. Yes? Anything? Anything anyone wants to say? Okay. Okay, I'll just do the right click. I'll go for simulate. I'll click. I'll select all the objects. Go to waveform window. Open the wave. Clock. See here now, clock we should not change again and again. So here it is forcing 1 by 1 value. Here directly we'll have a clock with 50%, 100 is the time period. So and is the first edge is rising edge. So we will just give this as okay. Reset initially I will give 1. I'll give D in also 1 to check that it is not giving me D in. If I give D in 0, then I'll not know whether it is reset active or it is coming through D in. And I will run it. So we can see here it is D in clock. Reset is 1, so we are getting Q as 0 as we said in a code. Now we will make reset as 0. Now we will run it. So you see here it is now D in is 1. It didn't change here because reset is just becoming 0 here. It will not take at this positive edge because it has to time. So now in the next positive edge, if we see, since it is 1, Q is also equal to 1. At the same time, actually, we should not change any input at the positive edge. It should change sometime before, otherwise it will not be reading that value. So reset just became 0. So at the next positive edge, you can see that it is nothing but D in. So this is what is a D flip-flop design. It is 1 bit. It infers 1 D flip-flop. And the important thing here is how to check this passage of clock. Now this is synchronous reset because only when clock will come, we will check the reset and then we are getting the output. We can have an asynchronous reset also, that we have to bring it over here itself. that we'll see later. Now one more thing here is, if I make D in as input 3:0 D in, input 3:0 D in, here again I have to make output reg 3:0, I'll make Q. So this no other thing, only the change will be here I should do 4 tick B 000. So it will infer 4 flops in hardware. We need, like how we have overlapping muxes, it will just create the same mux, that many bit size. It will create all 4 flip flops where D in 3 is going to Q3, D in 2 is going to Q2, D in 1 to Q1, and D in 0 to Q0. That's it. No other change will come here. So you can simulate this also and check. There will be no change. We have to give D in some values and it will pass it. So I just did this. Add wave, clock 50%, okay. Then reset. 1 second, I'll give force clock. I'll give here as falling as the first edge, so that I can show you this activity of this thing. Force 1, and I can even 1 second. I can give some period. Mhm. 1 second. I'll just give A here so that I can set the value. See now what we gave initially. 8 is, but reset is 0 because we didn't give, since reset is 1, Q will be 0 irrespective of A. Now I will give this as 0, so it will follow E in, and I'll run it. So as it is, we are getting A on the system. Is it clear? So this is what is the D flip-flop design. Any question from here? Is there any confusion? Yeah, I didn't get your question when we called an instance, because I already showed in that comparator, that is module instantiation. That code, that design should be in the same thing. If I just, okay, now we will see one 4-bit comparator counter design. We need to design one binary counter. We need to design one binary counter. I already gave you, I think, 3 assignments. One more, I'll give one sequential circuit. I will see one. I will see, design one binary counter. Binary counter is the circuit that can count 0, 1, 2, 3. We can have n bit. Let's say we are designing for 4-bit, so it will be 15. From 15, after that again it will be 0. Now one is a this is one is the traditional approach for synchronous counter. What we will do, we will write the truth table, present state, next state. We will say design it using D flip flop, and then we'll write the truth tables, K map, and then we'll get that. But here we'll follow some behavior modeling and algorithmic way, and the basic idea of how we can infer the structures. So we can design any number of bit counters, whether it is mod 16, whether it is mod 8, whether it is mod 20, mod 69, mod 100. any counter can be designed easily. So now for this counter, the basic thing is we will be having D flip flop because it has to control the flow. So I take this, and this is the input Q. Since it is 4 bits, so I'll be having this 4 bit here, 4 bit here. Again, we will take one input as clock is our input, reset is our input. If reset is active, we will again take reset as the controlling. If reset is active, we will get 0. So this will be 4 bit. So we have to give 0, 0, 0. Only when reset is not active. Is there any question? Is it breaking? Am I audible? Am I audible? Okay, when reset is 1, we will get 0.
Yes,
Now,
sir.
if reset is 0, what should be our next?
Continue.
Yes,
You are audible.
am I audible or no?
Yes, yes, you are audible, ma'am. You can continue.
Okay, thank you, ma'am. Okay, so it's when reset is 1, we are getting directly 0 because here it is 0. And again, see, this is 4D flip flop, 4 2 is to 1. That's why I'm writing here as 4 bit. So it will be 4 0 0 0. This is 0 0 0. Now, when reset is not active, what should be our next state? It should be 0 0 1. So what we will do, we will take a feedback from here, we'll give it here, we'll use one incrementer that is plus 1, and we will feed it here. So if reset is 0, it will take this as 0, 0 plus 1, we'll get this 1 here, we'll get this 1 here, but this 1 will come here only when the next positive edge will come. So during this positive edge, this is the first positive edge, during the next positive edge, I will get 0 0 1 here. Now this 0 0 1 will come here, plus 1, it will become 2, it will become 2, but this 2 will come here only when the next positive edge will come. So we'll get 0 0 1 0 positive edge. This 2 came here, this 2 came here, this will be 3 3, but this 3 will come here only when the next positive edge will come here. So 0 0 1 1. Similarly, we will get 1 1 0, that is 14 14 will come here, 15, this 15 will come here when the last positive edge will come here. Now this 15 came here. Now 1 1 1 plus 1, it will be 0 1 0 0 0. We'll discard the carry because we are using only 4 bits. So this again becomes 0, and we will get 0 0 0, and this continues. So that is how our counter will work. Now the same thing, we need to code it. So we will try to code this now in the Verilog. Counter 4 bit binary I will write because I am doing the basic counter design 4 bit binary, and I'll change it to again Verilog. Okay. So again, it is module counter underscore 4 bit underscore binary. Then we have input. Again, inputs are clock, comma, reset, comma. We have output as 4 bit. Since it's a 4 bit, I'll take output as output. Again, since we'll be using all procedural blocks, so I have to declare output as reg 3 colon 0. Since we are designing 4 bit counter, we take output as count. You can take SQ also, whatever is the name you want to give. Output as this. We'll use one procedural block always at pause edge clock. We code the same way like how we did there. So pause edge of clock only is our block when it has to trigger. But once this trigger, it has to obviously check reset. If reset is 1, we'll check for reset. If reset is 1, count is assigned to 4 pick the 0 0. Else count is assigned equal to what was our count. This count is nothing but we are taking count, we are doing plus 1. So it is nothing but count plus 1 and module. We will save it. And then again, we will save it. I'll just close it. We'll go to model sim, we'll compile it. It's successful. We'll go to library. We'll go counter 4-bit binary. We will simulate it. We will add weight. We'll just tweak this so that we can read which input is what. We'll post the clock. Sorry, I used the number. We'll post clock. We'll take this. Okay, we'll take the reset. First value I'll give reset as 1 itself. We'll make the reset active so that we'll get 0. So we say there is no change. We see here, we'll make reset as 0. And we will see here now. You can see here 2, 3, 4, 5, 6, 7, 8, 8, 9, 8. I can change it to binary also. Binary, or we can use this unsigned decimal so that we can read it 10, 11, 12, 13, 14. With every clock we are counting 15. And now the next is 0. So it is 15. And then as soon as it reaches 15, next clock it becomes 0 and the count continues. 1, 2, every clock you can see this thing like that. It will work as a 4-bit counter. Now suppose you need to design a 5-bit counter. I just need to change here to 4. I just change here since I'm doing 5-bit. I'll just put here as 5 here. I'll save the design. I'll close it. I'll close the previous simulation. Otherwise, I'll get the same thing. I'll compile it since I did one change. I will go to library. I will simulate it again. There is some errors or what? I'll select it. I'll go to add weight. I'll just make to read what is what. I'll force clock. I'm not changing. I'm just taking the default values. If you want, you can change that and see. So again, I have forced it 0, so it is 0. Then I'll force it to 0. I force 1. Output is 0. Now you can see here 1. I'll again change the count to the radix to unsigned decimal, so I can read it 2, 3, 4, 5, 6, 7, 8, 9, 16, 17, 19, 21, 22, 24, 25, 26, 29, 30, 31, 0. It is 31 and now it is 0. So this is the way, and what change will come here is this will change to 5. As previous design, it was 4 2:1 mux, 4 overlapping muxes. This was 4 D flip flop. Once this is changed to 5 bit, this will become 5 2:1 mux, and this will become 5 D flip flops in hardware. This is the change. Like that, you can go about 31, 32, mod 10. Suppose mod 10. You have to do what change I will. Mod 10 I will show you so that later we can give you some more counter design to do it. We will just go and see the mod 10 design one. Mod 10 means, again, if I see here, if reset is 1, we have to change. But as soon as 9 comes, already whatever we have done is correct. We took D flip-flop, we took flop, we have reset with us. If reset is 1, we are forcing 0. If reset is 0, we were forcing +1. But this, as soon as 9 comes, again it should go to 0. Again, as soon as 9 comes, we should go to 0. So it means we need to check one more option of count equal to 9. So we will put one more. Whenever the option comes, put 1 marks. So here we will check whether count is equal to 9. So now if count is equal to 9 is true, again 0 should come, otherwise +1 should go to the output. So it is same thing. When reset is active, we will get 0. When reset is 1, the 0 will come here. This is not equal to 9, so 1 will come here. This 1 will come here only when the clockage will come. Then 2 will come. Similarly, 4 will come. As soon as 9 will come here. Let's see, 8 came here. So 8 came here. 8 plus 1, 9. This is not, so we'll get 9. We'll get 9. We got 9 here as the positive. Now this 9 came here, but count is equal to 9. This is true, so we'll get 0 here. This 0 will come here, but the next positive edge only it will come. So after 9 we got 0, and this will continue from 0 to 9. This is how you can change in the counters, and you can design any counter. This is the hardware change. The same code I can change it. I will not write the new code. I can change it to the same code. See, whatever we have 2 marks now. First marks is already with us. We need to just input this marks. That depends, and the condition is count equal to this. So I'll just write it over here. So since we are having more than one condition, I'll use else if here. Else if count equal to 4 pick 31001. I'll just use since it's a BCD counter, I should not go for 5 bits. I'll just use 4 bits here. 4 pick 100, else it is count +1. I'll save it. I will go to compile. There is an error. Syntax error near else, unexpected else. Oh, I didn't define count. Sorry, COUTNT count else equal to 4 pick B, because we said that if it is true, we have to give some value. So it is 4 pick B 0, else count is count +1. I'll save it. Same thing what I code. If this is equal, we have to force count to this value, else +1. So I didn't write that part. So it is count +1. Save it. Project. Close this. Compile selected. It is correct now. It is successful. We'll go to library. I'll select this. Simulate this. Yes. No. Now this again, I'll select it. I'll go add wave. This is done. Now I will just make it with clock. I'll pose again. Sorry, cancel. Pose clock. Period is 100. Duty cycle is 50. If you want, you can give period is 200. Duty cycle is 60, 40, whatever. But normally clocks are preferred with 50% duty cycle. Reset again. Initially we will give it as 1. We will give it OK. We will run it. So it will be 0 itself. Now I'll give reset as 0. One second, I'll just make it 100 nanoseconds because it is easy for us to read it. I made initially, so it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So we can see here 9 and then it is 0. So it is nothing but BCD counter. So in the same counter design, we designed 4-bit binary, we designed 5-bit binary, we converted it again to BCD counter. Now for your assignment thing, you need to design one up-down counter. Up-down 6-bit counter. 6-bit binary counter. Then you have to design one mod 19 counter. And this is till here we are done. Any confusion? These are all the basic blocks for all the design. Once you know this, you can design anything. Anything else? One more.
Is there anything
Is there anything else you want me to do?
Is there anything else you want me to do? I think now knowing all this, you can design for any from a small block to a big block for any design, be it a combinational or sequential. And one more thing we missed is that FSM, finite state machine, using delay or more. But since that is also a research topic of its own, we thought we would just limit it to only these few blocks so that it will not be an issue for any of us. And again, I am telling, we just showed it in the model sim, but it can be done on anything, be it cadence or synopsis. Because the only thing is, as we all know, tool is not intelligent. Whatever we give in as the input to that, it will just take and it will do the simulation. So it is up to us to write a proper code, thinking of hardware, not like the other way how we do for other software languages like C or C++. Since all these are doing with respect to the hardware, this is a hardware description language. Hence, we should think of hardware and then write the code. I think hope this session was useful because we were showing you the hardware blocks and parallelly we were coding and showing the simulation. Any questions? We are open. This is not a part of the assignment. We always try to play with this Verilog code. If you people are crazy of now after learning this, you can write a small code like how to count the number of zeros separately and count the number of ones separately, and together you can count the number of ones and number of zeros also. Just we can start with all these playing things so that you'll also feel this useful. So if there is nothing from for us, we can stop here, madam. Dr. Jalja. You can coordinate all assignments. Will I announce 1 second?
We are giving all the assignments in the chat box. Please check and please check once.
Dr. Jalaja, madam, madam. Hello. Today afternoon will not have any session because all these assignments need to be submitted today and uploaded to whatever link madam will share. Is this fine?
Good afternoon, all. We are starting the quiz. You can observe the chat window, and there one Google form will be shared. That is a quiz Google form that you can submit within half an hour. All are multiple choice questions. And you're supposed to submit the assignment, morning assignment. Along with the quiz, you're supposed to submit the assignment also. 3:40, I will be closing this quiz Google form. Last 1 minute. I will close the Google quiz form.
Madam, Google Form link we not getting, madam.
Yes, sir.
Google Form. This question
Pardon?
for link.
Pardon?
Google Form, this question bank link we are not getting, madam. In chat box you are shared, na? It's not coming, madam. I'm waiting for the link.
No, I already circulated now. 310 itself. 38 itself I have circulated.
Oh, in WhatsApp group, that group, na, madam.
Not in WhatsApp, sir, in WebEx only. Because I'm recording that.
Okay, in WebEx chat group is not actually it's not come, madam. Chat box memory is not there. Actually, whenever connected from that time onwards, it will show the chat.
It is there.
Previous
You
chat
can
it will
see
not.
here. It is there at according to this time. 1 second. The people are submitting now, sir.
It's okay, madam.
You're from which college, sir?
I am from
Oh.
Varangal. Yes.
Why you are not come to the lab?
No, madam. Actually, while allotting room, it's vacant time late. 3 o'clock happened here itself.
Okay, okay.
Okay, madam. Then no problem. If it is mandatory, in WhatsApp, I will write. So,
Madam, can we leave the meeting?
Yes, sir.
Thank you, madam.
Tomorrow also you're supposed to join at 10 o'clock. So followed by the afternoon will be the valedictory. Thank you, sir.
Thank you.
Anyone still attending the quiz? Can we wind up?
Whereas in case of for loop and all, so until a condition is satisfied, the value will be assigned. Whereas in case of for a where, it will assign continuously. It will go up to infinity. For loop, so this assign statement will be only a finite time. Whereas in case of for a where, it will go up to infinite. So initially t is equal to 0, these are the values. After 100 nanoseconds, we are making reset is equal to 0 so that it will recognize the D input. Here for this, whatever this D, Q becomes simply 0. here Q depends upon D. So what is the D we have given? Initial value of D was 0, and for every 20 plus 40, total 60 nanoseconds. And here 100 is there. Okay. Total 140 nanoseconds. So we will get D is equal to D bar. Then always for every 10 nanoseconds, the clock will be complemented. The meaning of this one is clock becomes clock bar for every 10 nanoseconds. These things you can see in the test bench waveforms. You can see that the reset was initially at t is equal to 0, reset was 1. After 100 nanoseconds, reset was 0. So that you can easily see here. So up to 100 nanoseconds, reset was high, then reset is 0. When reset is high, what will be the output? As I have told, output is equal to 0.